Hi folks, this is Mundan Raghavan. So today the topic is big O notation. It is one of the important topic when calculating the algorithm's efficiency. So the basic introduction about big O notation is check the efficiency of the algorithm when the amount of data increases. And basically we will consume or we will use the time and the space when we use the algorithm. So we need to calculate this, how much time and how much space we are utilizing when you use the algorithm for the given n input. So if the n is less, then it may be working differently, but if the n increases, the algorithm's efficiency changes. So for that, we are just calculating the algorithm efficiency in the three different cases: best case, worst case, and average case. So when, let's say, we are the given n inputs, it is n is huge. Then if you try to find some value, for example, if you find the value from the given set of array or data, then let's say you find the data at once when you enter into the loop, so that will be the best case. Or if you are finding that data in middle of the iteration, then it will be the average case. But unfortunately, if you find the data at the last element of the array, then that will be the worst case. So generally big O notation focuses on or considering the worst case, and we will calculate that. The big O notation, some of the big O notations are shown in the diagram. So O of 1, O of log n logarithmic, and O of n linear, and O of n log n logarithmic linear, and O of n squared, it's quadratic, and O of 2 power n, it is exponential. And the reference shown in the slide. First we will focus on the constant. So if you consider this int example is equal to 1, so how much data you are feeding to that program or algorithm, it does not matter with this line. So this line will not use any of the data or iteration, so it will be the constant for any execution time for any given n inputs. So that's why it is a O of 1, and the relevant graph is shown in the figure. And next one, big O notation for O log n, logarithmic. Example, binary search. So logarithmic are the inverse operation of exponential that we know already. And in basic way, if you consider the logarithmic growth means, for the given iteration or the given data, if n increases, there will be a very slight increment in the operations. So if you see the sample binary search, let's say we have 7 values and we want to find the value 6. So it will take the median and it will compare with that median. If it is greater or lesser, based on that, one half will be reduced, then another half we will focus. Then after again we will find the median and we will find again we will compare for the given value. If it is greater or less, based on that, one half will be reduced from that. So for example, for every operation, half of the data will be removed from that loop. So that's why at the third step we will find the data, or we will come to know whether our value is present or not. So for example, if you have 3 data, then you will do 2 operations. If it is a 7 list of data, then it will be 3 operations. And if it is 15 and 4 and it is 100, then 7. So which means that if your left side, the value increases very drastically, but in the right side, it increasing very slowly. So this is one example of logarithmic notation. And given input size of n, the number of steps it takes to accomplish the task are decreased by some factor with each step. So it decreases, as you saw in the diagram, and the value is inside the right side, it will be increasing very, very slowly. So and the relevant graph is shown here. And next one, ON, it is a linear. So let's say you have array value or the list of values, you want to iterate everything. And if you iterate everything and do something on the time, for a given constant time, and you will be applying that process for every element for the n. So let's say if the n is 5, then you will do the action for all the 5 elements and it will take some approximate time. And if it is 500, it will do the for all the 500 elements. At the same time, the time also increases. So which means that for the given n value increases, then the time also get increases. Next one, logarithmic linear. So we already saw what is logarithmic and what is linear. So this code will be like a combination of logarithmic and linear. So for this, we can get an example like merge sort. So merge sort work like it will divide or it will be divided one by one, or two sorted list it will divide, then again it will divide by two sorted list, again it will divide sorted list. So after that we will do the sorting and we will, so for example, it will divide at the continuously and from the starting, then after it will do the sorting and then merge it. So that's why it's called a merge sort. So in this overall process we will do the logarithmic action as well as the linear action. So linear means for every input we will do some action, and logarithmic for the, let's say if the action, some actions will be done, it will be off for every line. So for better understanding, we need to understand merge sort individually. But as of now, in a simple words, we can consider for any process which contains the linear and logarithmic combinationally, then we will go for the O n log n. And next one, O n square quadratic. So if you have the two loops, or there is a loop inside the loop, and if you want to do the action, let's say you have the n is equal to 3 elements, then you will be doing 3 into 3 9 times. So for example, 0 1 2, for 0 it will take 0 1 2 for the inner side loop, for the same thing for 1 0 1 2 for inner side loop, and 2 0 1 2 for inner side loop. So which means that if you give n, then the total process will be done for 9 times, which means that n power 2, which means that 3 power 2 is equal to 9 times. So the relevant diagram shows in the slide. So some of the other things are O2 power n operation run on exponential time. So you can consider the traveling salesman problem, or you can consider the exponential in a general way. Is like if input increases very slightly, but the output or the process will be increasing very dramatically, or it will be very exponential, you can tell, but it rapidly increases in a predictable way in a single line. And O n factorial, it is for all the permutations you want to see that for the n elements, then that will be comes under the notation O n factorial. So example, again the same thing, traveling salesman problem. So we need to understand the traveling salesman problem to get into this, but as of now we can consider the O2 power n is exponential and the n factorial also exponential almost, but it has more value than the 2 power n. So this is the complexity chart. So if you have O of n or O logarithm n, then that will be good or amazing. And after that, it's O power n, it's fair. But after that, O n log n, O n square, O2 power n, O n factorial, these are the very increasing order, and it is very bad for any algorithms. So when we choose the algorithms, we should consider these things, and whichever in the good or fair, in that range we need to go. If you use the other algorithms, it may take more time and more complexity, and it utilizes the more memory space. So this is a very basic idea about the big O notation. In simple words, the big O notation is the measurement unit for the complexity in algorithms. So that's all. Thanks all. Thanks for watching. Subscribe my channel. Have a nice day.